In part 2 of Notes 12, we took a look at our rainfall dataset, and we saw that if we used our original rain variable, neither our normality assumption or our equal variances assumption was reasonable to make. So we wouldn't have been able to do a hypothesis test or make a confidence interval and feel very confident in those results because they weren't based on the conditions that we needed to be true for them to work appropriately. However, after transforming our data, we were able to see that if we looked at the natural log of the amount of rainfall, that actually did meet the assumptions that we needed to meet. So to reiterate, for the equal variances assumption, we did a hypothesis test to see if this was a reasonable assumption. And our two hypotheses, the first one is the null hypothesis that says our population variances are equal. The second is our alternative hypothesis, which says the population variances are not equal. And just like every other hypothesis test we've done, since we got a large p-value, quite a bit above 0.05, that means that we do not have enough evidence to say that the alternative hypothesis is true. Now, just to reiterate, this doesn't mean that the population variances actually are equal, or even that we necessarily think they're equal, but since we haven't really been convinced that they're not equal, it at least feels reasonable for us to assume that they are for the sake of our test. So we've met that assumption, which means now we've actually met the normality assumption and the equal variances assumption, and we might want to actually calculate a confidence interval using our log transformed variable because that was the one that met our assumptions. So remember from part 2 I added that variable to our data set and I checked my assumptions using proc t-test. I'll run this same code and I'll just add alpha equals 0.05 since I want a 95% confidence interval. And some of you may be realizing right now that I actually don't need to add that because that's the default that SAS will use even if it's not in there. But I just wanted to be very clear that that's why I'm getting this 95% interval. If I changed it to alpha equals 0.01, for example, I could get a 99% interval. And at this point, we're just going to go ahead like we did when we first started looking at confidence intervals. I want a confidence interval for the difference between the seeded and the unseeded clouds. So I'm going to go right down here under 95% CL mean on this first row that says diff, and this is going to be my confidence interval. 0.2409 on the lower end and 2.0467 on the upper end. So I could write that out. That is a 95% confidence interval for the difference in population means, but it's population means for log rain, which remember, rain was measured in terms of acre feet, so log rain is actually measured in terms of the natural log of acre feet. And if I tried to interpret this confidence interval, I could do this like we've interpreted intervals in the past. I could start by saying something like, I'm 95% confident that the population mean rainfall is greater for, this would be the seeded group minus the unseeded group. So since this is positive, I think the seeded rainfall was higher. And so I would say I'm 95% confident the seeded clouds have a higher population mean rainfall by between 0.2409 and 2.0467 natural log of acre feet, since that's the unit that this confidence interval was using. And the problem is that most people here would probably be a little bit confused because we're not used to using the natural log of something as a unit of measurement. For example, if I told you that basketball players were, 0.2 natural log feet taller than hockey players or something, you probably wouldn't have a very good idea of what that meant because we're used to talking about feet. We're not used to talking about natural log of feet. So what we like to do in these cases is we want to be able to tell someone what we've discovered in terms of that original variable that we were measuring. And that we call that undoing our transformation or back transforming. And so if I use the natural log function, the way to undo that is with the exponential function. We saw previously that the natural log of e to the x is just x. So the natural log is sort of undoing e to a power. And we could reverse that around. E to the natural log of x is also just x. So e is sort of undoing the natural log. We can think of it like squaring and square rooting. We can go back and forth with those. So what we're going to do is we're going to use this exponential function to back transform our confidence interval. That means I'm just going to take my lower endpoint and I'm going to do e to that power. I'm going to take my upper endpoint and I'm going to do e to that power. And I would get this interval now. So 1.272 up to 7.742. And there's some good news and bad news here. The good news is I can start to talk about things in terms of acre feet again. So I'm back to my original units. However, we have sort of a price we have to pay for doing this. Originally, our conclusions were all about population means. Once we do a log transformation and then back transform at the end, our conclusions are now about population medians. All right, so it's not exactly the same as it was before. There's an additional thing when we're looking at two independent samples. So instead of being able to talk about the population mean 1 minus the population mean 2, our conclusions based on this interval are actually now about the population median for group 1 divided by the population median for group 2. So this interval actually represents where we think median 1 divided by median 2 falls. One of the common mistakes that people make here is they want to think that one of these numbers represents median 1 and one of these numbers represents median 2. That's not the case. So before, we would have looked at this and we would have said, this represents the range that we think mu1 minus mu2 falls into. This now represents the range that we think median 1 divided by median 2 falls into. So what we can do with that is we can start to look at these numbers and think about what they're telling us. Now, if I have median 1 divided by median 2, and that ratio equals 1, the only way that's going to happen is if these are both the same number. So say median 1 is 5, well, median 2 would also have to be 5 to get 5 divided by 5 equals 1. So if this ratio is 1, my two medians are the same. If this ratio is bigger than 1, the number on the top must be bigger than the number on the bottom, so I would think median 1 is bigger than median 2. And if this ratio is less than 1, the number on the bottom has to be bigger than the number on the top, so I would think that median 1 is less than median 2. So what we're going to do coming up on the next page is we're going to look at median 1 over median 2 and think about what our interval's telling us. In this case, all of the numbers in this interval are bigger than 1. So if I'm looking at these three possibilities here, I don't think that my two population medians are the same because nothing in this interval contains the number 1. And in fact, all of these numbers are above 1, which tells me that I'm going to be pretty confident that the population median for group 1 is bigger than the population median for group 2. So we'll revisit this in the next part of the video. One thing I want to note before I do move on though is some of you may be wondering, well, why does our analysis change from population means to population medians? Why did we go from talking about a difference to talking about a ratio? There's some math behind it. I've posted a file on Moodle that explains why we change our interpretations in this case. If you're curious, I encourage you to check it out. I'm happy to answer questions about it. But I also just want to let people know that you're not responsible for knowing why this is the case, as long as you can remember that it is the case and how to use it for interpretations.